Okay, it looks perfect. Perfect, yes. David. No problem.
Okay. Now I can, should I turn off sharing? Do you want to show something you're showing something before my talk, right?
Right.
Okay,
maybe,
so,
who is the host? Maybe you can share the program for today first. Who will be the host?
So,
is it Samuel?
Well, I must have some hosting ability because I just shared a screen.
Yeah, I would like somebody to present the program of today first. Can you do that? Somebody?
Yes, I can do it. Wait.
Okay, or is it you? I see. Okay.
No, actually, probably I can do this.
I see that.
Yeah, so this is David, our program. So we'll be start at 8:30, so in 5 minutes, and then there will be opening remarks first, and then your session will start around in 8:50, so 8:50 p.m. in yours. Around 45 to 60 minutes, it should be okay. And yeah, is this
okay, David? Is this okay to you?
I can see this. Yeah, this is good.
Yeah. Is it okay? Can I now stop share this image or this program? Okay.
We still have 4 minutes left, so how do you want to do it, Asih? Maybe you can approach the attendance. We already have 131.
Today, the MC is going to be Mbak Fadilah, and then I will be moderating the discussion with Professor David. So I think Mbak Fadilah can open. Mbak Fadilah can open.
I think maybe in 4 minutes, Aika. So I think we just let other people to join. In 4 minutes, probably there will be some of them will join soon.
So maybe while waiting for the 4 minutes, I would like to everybody who is attending, David, do you allow me to do it in Indonesian, because not all of the attendants can speak English so well. So I'm a little bit going to introduce and say hello to everybody who's attending. Is that okay to you, David?
Sure, but are you suggesting my presentation will go continuously in English, right?
Yeah, of course.
Okay.
But after that, probably for the question and answer, I will encourage the attendants to, if they have problems with the language, they can ask it in Indonesian, and then the moderator, Asih in this case, will help it translate it to you. And then if you give an answer and it's not clearly understood, then probably Asih can also translate it for the attendants, because we don't want the language to be a barrier here. Is that okay to everybody here in the room?
Yeah, that's certainly okay with me. Yes.
Okay, so everybody in the room, we have 140. We have here Professor Benjamin Lumantarna from the Petra University. I have Dr. Insinyur Yoshia from the University Indonesia. I have Insinyur Anin Hudaya, who is not yet here. I have Hanafia, Dr. Hanafia. It's very dark, your screen. Ahan.
Okay.
We have Hanafia here, and of course we have we have our queen, Dr. Januarti. Hi, Jani.
Hi, morning. Good evening, David.
And we have Devi Sukamta, and then of course our beautiful MC. You look great, Asih, today. You look very, very beautiful. And then we have Anjar. He's our webmaster, and he developed actually the web for today's event. Then I have Fadila Muslim, who's also from the University of Indonesia. She will be the MC, right, Fadila? Okay, and then we have David, of course. And beside him, we have Faimun from the Technology University in Surabaya. And then there is Samuel, who is from the HAKI. And then we have the Secretary General of HAKI, Dr. Dina Rubiana Widarda from the University in Bandung. I have Mr. Budi Antara. His screen is not yet on. We have Dr. Nathan. We have Dr. Johnny and Dr. Gedepri Gana. I'm hello, Kohanin. You're still on mute.
Hi, everybody. Good morning.
He's the big boss here. Okay.
No.
Yeah, you are. Okay, we already reached 8:30, so I'll hand it over to the team. Thank you, everybody, for attending, and thank you for everybody who worked so hard. Let's go. Go.
Yeah. Okay. Thank you very much.
Recording in progress.
Professor Heike, for introducing and greeting all the participants here. So, Excellency, distinguished guests, participants, ladies and gentlemen, good morning, selamat pagi, and also good evening for those in USA. Prof. David, also probably some ACI representative who also already attend or join us. Assalamualaikum warahmatullahi wabarakatuh. So welcome to join webinar on high performance concrete in Indonesia, hosted by Himpunan Ahli Konstruksi Indonesia and also American Concrete Institute or ACI. Today, as you already know, we're also going to do a HAKI-ACI dual membership launching for the first time. My name is Fadilah Muslim, and I'm actually an assistant professor at Civil Engineering Department, Universitas Indonesia, and I'm very pleased to be here this morning to be your MC in this webinar. Okay, now let's begin this program with an opening remark from HAKI Presidium, and it will be delivered by Dr. Januarti as HAKI representative in ACI. So, Dr. Januarti, the time is yours.
Okay, thank you very much, Dr. Fadilah. Good morning, everyone. Good morning, Indonesia, and good evening, United States. Distinguished presenter, moderator, and participants. My name is Januarti. I'm also a lecturer of Institut Teknologi 10 November. I'm online in Surabaya now. And I'm also a representative of HAKI in ACI. Our president, Professor Iswandi Imran, is still in Amsterdam. So right now, is 1 p.m. maybe, yeah, in there. So it is too early for him to join the opening, but he will join us after Professor Lange presentations. Ladies and gentlemen, it is my great pleasure and honor to meet you in this webinar, the launching of HAKI ACI joint membership, and also to provide my opening remarks. On behalf of HAKI, I would like to thank all supports from HAKI members. We appreciate Professor David Lange to give your time providing an interesting topic. I think I would like to ask more questions, especially your last slide is very interesting on 3D printing, the applications of SEC. Yeah, and I would like to express our gratitude and appreciation to our collaborators from ACI, Melinda and Marcella, and also our partner Bernie. He is not here now, but we appreciate this event as an opportunity to have benefits of being a HAKI and ACI member. There are more than 420 people who are interested in this program. I think Marcella and I are going to be busy after this event. I wish you enjoy the webinar and also enjoy having a double membership. On behalf of HAKI President, as the host of this program, I would like to open the event. Thank you very much and terima kasih.
Okay, thank you very much, Dr. Yani, for that wonderful remarks. Now, I would like to call our first speaker for the first webinar session about self-consolidating concrete. I believe all of you here can't wait to hear his presentation and also learn a lot from him. But let me share his CV or curriculum feature for your information. Wait. Okay. Okay, so our first speaker, as you already knew, that he's Professor David Lange. So he got his PhD in Northwestern University and finished his MBA in Wichita State University. Also, his Bachelor of Science in Civil Engineering from Valparaiso University. He's currently a Professor Emeritus at Department of Civil and Environmental Engineering at University of Illinois at Urbana-Champaign. He also, before that, of course, he also as a professor, he was also as a professor at Department of Civil and Environmental Engineering at the same university. And really at the beginning of his career, he was as an engineer at Boeing military airplane in Kansas. Okay, so this session, this first session will be moderated by Dr. ACI. Let me also share her CV for your information. Yeah, so Dr. ACI currently is lecturer at Institut Teknologi Bandung. She got her PhD from University of Tokyo and her master in Institut Teknologi Bandung and Nagoya University Technology, and her bachelor degree from Institut Teknologi Bandung too. Okay, so I think that's all about the information of our speaker and moderator. After Professor David Lange give his presentation, we will continue with a Q&A and it will be moderated by Dr. ACI. So Professor David Lange, the time is yours. And then we continue with Q&A led by Dr. ACI. Please feel free to write down your question on that column at any time during his presentation for all the participants who's gonna ask Professor David for during the Q&A session. Yes, Prof. David, the time is yours.
Okay, very good. Well, let's go ahead and get started. I'm going to share my screen. And I believe you can see the slides now.
Yes, perfect.
Okay, very good. Let's, first of all, let me start by thanking the organizers for inviting me. It's a pleasure to be here with you virtually. I'm literally halfway around the world, and it's amazing how technology brings us together. So my best wishes to your event here with this webinar, and particularly I want to give compliments to your partnership with ACI and this dual membership. The topic we are going to talk about today, self-consolidating concrete, fits very well into the webinar, which is on high-performance concrete. You know, back when high-performance concrete started to be a term used, high-performance almost always referred to strength. And this is back in the 80s, people were starting to talk about high-performance concrete. And later, adopted many other aspects of performance. And here in self-consolidating concrete, you will see that one of our primary concerns is workability as a performance attribute. And we're going to move through this story about self-consolidating concrete because it is a necessary story to tell how we get to 3D printing today, where we modify workability so that we can use extrusion to make shapes and so forth. There's many exciting things going on with concrete today, and those that deal with workability are among the most fascinating. I want to give credit to ACI. Of course, very much, ACI is an important organization to me professionally. I served as president of ACI in 2018 and had a terrific year of outreach. And I can tell you a couple things. One is that our international relationships, ACI holds these international relationships in the highest priority. So what you see here today, where you have a dual membership, is incredibly important to ACI because we're trying to find ways for ACI to share its enormous database, its enormous knowledge storehouse with different parts of the world. And that's why an organization like ACI even exists, that we're developing knowledge about concrete, that we share it as broadly as possible, and that we therefore not only increase the quality of concrete around the world, but we help ACI be a central part of moving forward the technology. That's why we came up with this slogan, always advancing. And I think that's a great slogan because it speaks to how concrete is today. We often many people outside of our field will think concrete is an old-fashioned material. We've used it for 100 years. No, it's not that. It's not your grandfather's concrete. There are so many new things happening with concrete, and self-consolidating concrete is an example of that. So let's start with some of the benefits that we have with self-consolidating concrete. Well, the first thing we want to say is that, I want to go back here, and I didn't mean to advance it. I wanted to get my cursor going as a highlighter. Okay, does it work now? Yeah, it'll go now. Okay, so of course, the first benefit of SCC is that we get good consolidation without vibration. It flows without segregating. If you were only familiar with old concrete and you heard that you were making a concrete that could consolidate by itself, you would immediately say, you must have too much water in it. You must be putting too much water in. That's not how we're getting the workability. We're using gradation of aggregate. We're using admixtures. If you just put in more water, you would have a terrible segregation problem, and it would be terrible concrete quality. So what this new concrete does is it flows and moves, but it's a good, cohesive concrete, and it does not segregate. It fills confined areas of formwork. It fills where you have high congestion of rebar. It provides excellent form finish and detail. And because you're pumping, almost always these are pumping operations, right? And those pumping operations will tend to be relatively low labor cost. And that's another advantage of this kind of concrete. So here you see two videos. It's an amazing thing that concrete can have such a large range of workability. So on the left side, you see paving concrete, which is immediately stiff enough to hold its edges if you cast the pavement. And then on the right side, you see the self-consolidating concrete. Now, I would add one thing about what you see on the right. I would not say that self-consolidating concrete is best used for flat work. We normally don't do it that way. If you're making flat work, you probably need to have a better finishing surface. One thing you would get with SCC is a kind of a cohesive, perhaps even a little sticky surface. It's not really the best material for flat work. But for many other things like filling piles and filling foundations and filling where we have very high congestion of rebar, those things will work well with SCC. It opens the door to creative architectural shapes, such as you see here. The tower on the left-hand side is a relatively new tower in Chicago called Aqua. Does it look like water to you, Aqua? That's the name. And the architect did her undergraduate at the University of Illinois. Jeannie Gang is her name. Finished surfaces. The wall that you see on the left was part of an Illinois DOT project in Peoria, Illinois. And these sound barriers were, there's always interest in trying to upgrade and have a more beautiful infrastructure. And so these designs are placed into the forms. And you need something like SCC to have the detail of those forms. In the middle there, you see SCC versus normal concrete to create a very good, clean, finished surface. So if your project is requiring architectural detail, SCC might be a good solution for that. Now, SCC is also one way we're going to do it. We need to improve our language about workability. And so we're going to have words like yield stress. You might think of this as slump. And plastic viscosity is sort of the flow property, the viscousness, the viscosity of the material. And I have a zone on the chart showing normal concrete. And SCC is in a completely different area. And you notice, what is the biggest difference between the zone of behavior by normal concrete and SCC? Low yield stress. That is, this is the way we can technically describe the tendency of the material to flow under its own weight. So this, of course, opens some questions about how do you measure these things? How do you define SCC? And we'll talk about measuring that too. So let's go on. SCC versus normal concrete. SCC is different than normal concrete. Normal concrete would be concrete that we make by following the guideline in ACI Committee 211. This is our normal mixture proportioning guide. And when we started doing research on SCC, we did a literature review and found all the different mixtures that we could find that represented SCC in literature. And then we analyzed, or we found, the fine aggregate to coarse aggregate ratio and the aggregate content. This zone is a zone that is normal concrete. Aggregate content is about 75%, and then paste content is the rest. And the fine aggregate to coarse aggregate ratio is shown here as about 0.7 or so. But all these other mixtures out here lie outside of that zone, indicating that SCC is a different kind of material. I also want to say that notice that there are some SCC mixtures that in fact share this attribute of FA, the fine aggregate to coarse aggregate ratio, and the aggregate content. So SCC is still concrete, and it overlaps with the zone that we have as our normal concrete. But you're going to want to design your mixture to meet the needs of your raw materials, your admixtures, and the needs of your concrete producer, how they're doing the mixing and so forth. This particular chart on the bottom shows the proportions of a regular mixture with cement, water, air content, fine aggregate, coarse aggregate. And you notice that the biggest difference here is that, well, first of all, cement and water might in fact be the same as a normal mixture, but there's a new volume of fine aggregate. And these fines are a popular way to achieve better cohesion and therefore better workability control and better fluidity. So this is one way that SCC is often designed, to have a population of particles that are even kind of extra fine particles. So the mixtures might be different. Now, in practice, what you want to do is develop these mixtures in collaboration with your local concrete supplier. they're interested in learning how to make this too. This is a marketable material for them. And so they want to invest in their time, energy, and effort to make a good SCC mixture that works well. The other source of expertise for coming up with this mixture would be your admixture suppliers. Whether you're using suppliers from Sika, Master Builders, BASF, these professional companies serving the concrete chemicals area have expertise that is very important for coming up with good mixtures. So I make here a few notes about SCC. You're going to have higher paste content. That means lower coarse aggregate content, but higher paste content, higher powder content, a little bit lower water, usually smaller coarse aggregate, higher sand to aggregate ratio, and you will be using chemical admixtures that you don't use every day. These chemical admixtures like viscosity, modifying admixture, you don't use that in regular concrete. And so these things together with the attributes above here can help you achieve that workability without segregation. We're going to also need new ways of doing testing. The most popular way to do testing is slump flow. Slump flow is using the same kind of cone that we use for the slump test. But the spread of that is a big patty, such as you see over here on the bottom with the J ring. So the patty is measured from side to side. The diameter of the patty is our measurement when we do a slump flow test. But we also have some of these other tests that are in here as well. So these tests, where do you find out about these tests? ACI Committee 237 has guidelines about all these tests. ASTM has identified test methods for the things I have on this page. So you don't have to be concerned that you don't know where to go for the instructions for these tests. They've already been defined. And so by doing some homework, especially now that you have this dual membership, I'm presuming that you're going to have new access to ACI's library. And that means you can go to ACI 237 and find the guideline for how to make SCC. That would be a good place to start. Okay, I wanted to just show an example of how you might fill a complex form that you can't fill with normal concrete. This was a case that we did with our colleagues in mechanical engineering, the University of Illinois at Urbana-Champaign, that's UIUC. And my friend in mechanical engineering does research on explosive materials, and he needed to make a blast chamber. And so he was working with other people on this, and they came up with a design of a big box. This box is, I think it's 4 meters by 4 meters by 4 meters, a big box. The wall is about half a meter thick. It has a two-side, it's a steel form that is hollow. And what you see in this photograph, this photograph over here, this is looking down into the chamber, into the wall. And you see all these shear studs. That wall is hollow, but it needs to be filled up with concrete. And so on the lower right, you see the worker guiding the pump from outside. This was a silo, by the way. This in the Midwest, we have a lot of grain silos. And so the grain silo was selected as a way to build a house around this chamber. So the blast chamber is in here. I'm coloring my blast chamber in red. Okay. And then the silo just is around the outside to give an environment for it. But this man is inside, standing on top of here with the pump hose coming down, and he's directing it into one of these little holes at the top. And this goes down the wall, fills through the floor with nobody able to watch it, fills up the floor, fills up the walls, and finally fills up the roof of the chamber. And at the end of it, we see the concrete filling these holes that, we're filling the whole thing from one corner, but it finally becomes apparent here. We did this in about 2 hours, 3 hours, and filled up this whole thing. How do we do this? SCC. We could almost have done it no other way. So this was a great application for filling a complex form with SCC. Another area that SCC is very good for is rapid construction of tall walls. And this was a hospital in Peoria, Illinois. And this was an excavation in the side of a hill. And this area in front of us is going to be the interior of the hospital. And this is on the outside of this is ground in the hillside. And in fact, you can see me. I'm standing right there, talking with somebody and observing the construction. So this is about 15 meters tall. We made a section of wall from here to here. We filled this wall 6 hours and no vibration down in the wall. Everything was self-consolidating. And we wanted to of course, the construction crew had concern about the pressure. When you fill a wall this tall with a liquid concrete, you're concerned about the pressure against the forms. And so for the last 10 years or so, there's been a whole number of researchers measuring how pressure behaves with SCC. That's what this next part is about. Formwork pressure has been a key concern because SCC has much greater slump than normal concrete. That is, SCC has lower yield stress. Now, this idea about formwork pressure is an old topic. We have at ACI, we have a committee on formwork, and they give a lot of guidance about the lateral pressure of concrete on the forms. And it gives you expressions about how these pressures decay with time. And there's some math here that we aren't going to go into, but basically this is an idea about how the height of the wall and the time involved in filling, the rate of filling, are parameters that are used for prediction of pressure. And of course, you don't want to go too high. But in the end, this old advice ends up saying something very important. If you don't really know what kind of concrete you have, you just know it's highly fluid. ACI 347 says you must withstand full hydrostatic pressure. You have to build your forms strong enough to withstand full hydrostatic pressure. Well, that's a problem. That's a problem because hydrostatic pressure is, it means that standard commercial forms, the highest you're going to go, maybe 3 or 4 meters, and that's it. Your forms aren't strong enough to go higher than 3 or 4 meters. Well, that's not high enough. I just got done telling a story about how we need to go 15 meters. So how are we going to do this? Well, the way we do this is we do some testing along the way. If you have engineering advice and engineering insight to know what the pressures are going to be, you can go higher than hydrostatic pressure would suggest. So this is the issue. SCC does not behave as a liquid. By designing forms for full hydrostatic pressure, it's overly conservative. We can do better because this is the way the pressure really is. This is a line that represents hydrostatic pressure, but this is reality. We don't get up that high. The pressure stops somewhere in the middle. We need to know where that value is. So here's an example, sort of a little cartoon of how these pressures work. So on top, we have a fast filling form. On the bottom, we have a slow filling form. And here we fill it up. And this one, the measurement would suggest we have hydrostatic pressure. That is pressure that is linear and proportional to the height of the concrete. Go a little higher, we're hydrostatic. Go up to the top, in a fast fill, we're hydrostatic. This one, we're filling slower. We might be hydrostatic for a while, but after a little longer, we're not. And we'll see that the pressure at the bottom starts to become limited. And we go higher, it's still limited. Go higher yet, it's still limited. We never get up to these higher values. So this is what we're trying to describe so that we get permission to go to higher heights more rapidly. So we expect hydrostatic pressure, which you see again here. What we observe is not hydrostatic. It's some kind of a function that's different than hydrostatic. And it starts, I use the word decay. The pressure decays, it relaxes, it reduces with time. So what we do want to do here, this is, by the way, this is the chart of that 15-meter high project. And we had our delivery of concrete all day long over 6 hours, 360 minutes, 6 hours. And so we expected pressures or could have had pressures for hydrostatic that went up to a 200 kilopascal. And what we instead saw is that our pressures went higher for 2 hours. This is at the bottom of the wall that we're measuring. It went up for 2 hours. And then from the second hour to the sixth hour, look at this. The form is still being filled. It's still being filled. More concrete at the top. More concrete, more concrete, more concrete. The pressure at the bottom is already subsiding. So by knowing what this function is, our forms don't have to be higher. Well, you want them somewhat higher than this, but let's just say our forms can be 60 kilopascal and it will be safe if we can predict and know these behaviors. Okay, so controlling formwork pressure. This is another picture of the same project. These are just factors influencing formwork pressure. I want to just underscore that there are many factors that affect formwork pressure. You can see all these material properties, et cetera. And the most important one that you can control on the work site, boom, right there. How fast is your construction? If you can make your construction slow down somewhat, you can allow those pressures to subside. So we want to know what that function looks like. So this was an article we wrote, how tall, how fast, how safe. And it was a description of the project that I'm talking about, this project. And basically, here's what we're suggesting. Step one is we want to characterize the material, the characteristic pressure decay. Number two, we want to impose the variable pressure head that the project demands. How fast is the rate that the project demands? And so what we do to measure the decay is we fill a small column using sensors at the bottom to measure that pressure on a small column. Here's the sensors, little data logger. And we've done this now on several different kind of projects where we go to the field and we install these pressure sensors in the wall of the form. And we can measure the actual pressure. There's how it goes. So you can see the face of the sensor is on the inside wall of the form. So the concrete's out here. It bears on that surface. It measures the pressure. And our data logger chugs away and saves the data for us with time. And this is what we get. This is the data we get from that short column. We fill it up rapidly. This is essentially a liquid head, and the measurement right there is filled in a couple minutes, and we get our maximum pressure. And then we watch it. We leave it alone. And what do we see? The pressure decays. In 1 hour, it's dropped 20, 30%. 2 hours, it's dropped by more than half, and so on. Drops all the way down. When we have this value, now we can do some modeling, because we can presume to place heavier loads on top of this fresh material. And we get different pressure height column, the same decay curve, but different standard pressures are experienced with the height column. And temperature could even impact the pressure. You can imagine that if you go to high temperature, this is hot concrete. This is in Jakarta. There's your standard summer day. That's the standard winter day. And look how fast it decays. If you're now in Illinois, the same material, the pressure decay is like that. So we need to know what these conditions are to make the prediction work well. And even set altering admixtures like retarders and accelerators make a difference, as you can imagine. So we take this pressure curve, we can mathematically describe this curve, and then we can start predicting the overall pressure from the project requirements. So this rate is the project filling rate, the head pressure. And our model will predict that this is the pressure that we experience at the bottom of the form. In other words, we don't get to 25 PSI. We don't even get to 10 PSI. 5 PSI is the maximum of what we see in this project at the rate that we're describing. Okay. So this information is all included in papers, and it's also included in ACI 237 publications, where we have a guide for working with self-consolidating concrete. And I guess this is an obvious thing too. So someone might say in your company, well, I want to be able to pour faster. What will be the ramification on pressure? Well, if I go faster, I move this curve to be a steeper curve. The orange curve is faster than the red curve. And the orange pressure prediction is around 15, whereas the red pressure prediction was around 8. And so we can make a good engineering judgment about the economics of the construction. How long will the construction take? How much time do we need to cast this tall wall? And that's where the modeling can help you. Okay. So this is our field application I keep referring to, and here was the actual pressure head I've referred to, and here are the actual data from real sensors mounted in the wall at different heights. And we had our test measurement and our prediction. So here is a sensor located 1 foot above grade. And you can see here there is a measured pressure and a, what does that other one say? That was the modeled. Measured pressure and modeled, very similar. Measured pressure and modeled, they're very similar. 22 feet above grade. So this relationship of how the pressures decay are uniform no matter where in the project we are taking this measurement. Now, one thing you want to keep in mind is this. When we did those short little columns to calibrate ourselves, we had to keep it still. If we go up to that column and we shake it after 5 minutes, we will see it clearly. It's like vibrating all the concrete. It's you restore the fluidity to the concrete. And that is an issue that you want to be careful about in tall wall construction. Local disturbance can cause the pressure to return to hydrostatic. And this can be dangerous. Imagine if you have 15 meters of concrete and, imagine you had an earthquake. Jakarta has earthquakes, don't they? So now the whole job is shaking. Well, I'm afraid you have a vulnerability there. You have a safety issue. That concrete will reliquefy, and the pressure will blow out those forms, and you have your project has a big setback at that point. By the way, I saw that happen one time. I was up on top of the forms of a tall wall construction when we had a part of the formwork that had a T and had part of the wall going into a T, and the reinforcing at that point was not good enough, and it actually blew out the forms, and it was quite a sight to see. I think I watched about 3 trucks of concrete leak out onto the ground, out of the forms. And I thought it was an awful thing. Believe it or not, this is if there are people who work in construction online today, man, I am always amazed by people who do this kind of construction work every day. Did they let that stop the project for the day? No. They got people in there working to close up the gap, get the new ties in there, fix the formwork, and they by this time the concrete is gaining stiffness anyway, and we kept going, and by the end of the day, the project was back on track. It was really quite the thing to see. I was amazed. Okay. Field testing leads to ACI recommendations. Okay, so ACI let's see how we're doing with the time. We're fine. ACI committees are made up of professionals coming from academia or coming from industry. Lots of different people coming together that have interest in a topic. So 237, being a committee on self-consolidating concrete, we had people from the academic researchers and industry researchers and admixture companies all on this committee together. And the committee at one point says, what do we need to do to get to advance the knowledge of SCC, to make it better for people using this material in practice? And the one thing people immediately agreed on is we need better testing that works together, that people agree on. And so there is a type of test that we call round robin testing. Round robin testing is where different researchers, maybe you get 6 or so different labs, and they all come together using the same materials, and then they use their own devices for measurement, and you compare what way of measuring the property is better, and so on and so forth. So we were able to do that. So we got all the people interested in SCC, and we set up some large tests, field scale tests, where people could measure formwork pressure. And one of these was led by a fellow named Lloyd Keller. He's from a company called Ellis Don, based in Vancouver. Or Toronto, they're probably in both cities in Canada, and but he helped us set this up. And so we also had another test program in Stockholm, Sweden. This was organized by Peter Billberg, who I want to give credit to. Peter is the one who wrote the paper at the end, Peter Billberg. And then you see that these 2 main papers, this was on the test in Sweden, and this is on the test in Toronto. And so Peter, look at all the authors, Roussel and Amazon and blah, 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 all these guys, 15 guys. And so there's plenty of good thinking that interested in SCC behavior coming together in these round robin tests. And there you have the Sweden group and the Toronto group. Okay. And it's been a few years now. This is now 10 years ago. And so in the intervening time, SCC is now being moved into practice all around the world. I know, for example, since I've retired from the University of Illinois, I'm doing some work there, but I'm also doing consulting, and I'm consulting with a company down in St. Louis, where we're doing anticipating 50 tall walls going into a church, a new church building, a Catholic church. And the tallest of these are 50 feet tall. And so they immediately say, we're going to use SCC to make all these wall segments that are working together in the project. And so it's going to be very exciting. But they definitely had questions about what are the pressures like with the material we're using? How do we measure these pressures? How fast can we stage our construction? Okay. Here at the end, I want to do one more little topic that I just think is fun because it represents where this is going for the academic researchers mainly. You know, for those of you who are civil engineers, structural engineers, you know what finite element modeling is, FEM, and how important that kind of computer modeling has been for structural performance, structural behavior of tall buildings or any kind of structure. And FEM has been an available tool for, I don't know, it goes all the way back to when I was in college. So we've been using FEM methods at least, since the 80s, 70s, probably. But today, FEM is like standard operating procedure. You do everything with these kind of techniques. Well, the thing about FEM is it's not really directly capable of modeling liquid materials. It's okay for solids, elastic solid materials, but not for liquids. But there are other techniques. There's other things we can do for liquid-like materials. And one category of model is called discrete element modeling. Okay, finite element modeling, where you have elements tied together. Discrete is when the independent nodes of the elements are floating with respect to each other. All right, discrete element model is a class of model I'm going to describe here. And it's a particle scale numerical method. And it can simulate granular flow. Isn't that just what we're talking about? Concrete, that's a self-consolidating concrete, a granular fluid. And this kind of technique is very suitable. So we can simulate and analyze flow behavior and predict pressures in the system. And the way this works is the following. This is very simple. Just if you're new to this, we might have one particle here. We have another particle here. It has a zone of contact. How are we going to measure this contact numerically? Well, we can use these damp springs and dash pots. Remember that kind of thing? This goes back to like strength of materials or our physics behaviors. This is a viscous damper, this model, where we have the elastic and the viscous part of the damper. Okay. And we can even call this a liquid bridge. Okay. So we have the damping contribution, the frictional contribution, the elastic contribution. All these come together to describe something complex, that is the capillary force contribution for wet particles. All right, that sounds good, doesn't it? And you can do this. What we have here is a model of dry sand and the same model where the parameters are changed. So we're doing wet sand. And so you can see the sand pile is fairly flat on this one. And the sand pile is pretty stacked up. Why? Because there's wetness here. The behavior between particles is different. That's why when you go to the beach to make a sand castle, it needs to be wet and it behaves different. And this is exactly the kind of modeling that we get right in this simple case. Now we can use the L box. This is a test used for SCC. We stack up the concrete in the top part, and we take a gate and we lift the gate. So here we go. Lift the gate, the material flows. So here we have the case with the parameters for dry aggregate displacement, and here dry with low friction displacement, and which you get a different kind of behavior. Hello? Yes, does someone need to cut in here?
No, you can just continue. I think there was a mistaken voice going inside.
Okay. I just have maybe 5 more minutes. Only a couple more minutes here.
No, it's okay. You can continue. We still have plenty of time, even for question and answer.
So this is a model of SCC filling a column. And what I like about this kind of modeling is it captures some nuances of the behavior. You notice that the pressure is not constant. I mean, well, the pressure is a color gradient. So the high pressure red, lower pressure green, zero pressure blue. And we have zones of high, but right next to it, even below it, there can be a zone of a little bit lower pressure. And this is true in the way particles bridge and contact and bear on each other. It's like when you stack marbles together, but in fact, down below, there is a zone where there is no marbles. It can have low stress. Okay, so we can see the nice thing also about computer models is you can ask questions about the state of stress of the particles or the state of stress on the formwork. Those are different things that kind of bear on each other. Look at this. It's way down here at the bottom. There's some little particles that are blue. They're actually sort of trapped in a free zone where there's a bridging action over the top of it. That's very real life. We know that happens. You've seen this kind of a case. So it's neat to see that these computer models successfully predict what we see in real life. Here's another kind of a slump test where we are calibrating the results to some real materials. So we found some, this is always a question when you make a model, is it realistic? And we go through a process called calibration. And so we do a particle simulation. It shows how the particles might fall if we were to release them. But we also can do real particles and compare the predicted results with the real particles. And when we tune the model just so with the parameters being set and so on and so forth, we can get them to match right. And then the agreement between experiment and simulation is shown in this very simple case, a calibration case. Then we can go to complicated cases and use the model too. And this would be a case where it's a little more complicated. What is this? This is 3D printing. And so we're starting to think about how these discrete element models can be used for designing materials. This will help us understand what is the cohesion, what is how the particles behave with respect to each other to successfully do 3D printing. And that leads me to this last slide. This is a new area of interest. ACI has a committee dedicated to 3D printing. And man, all you have to do is read the civil engineering literature and you see people doing 3D printing all over the world. It's one of the most interesting things that has captured the imagination of our community. Students everywhere are being drawn to civil engineering because it looks like a field that is actually sophisticated, advancing, using new technology, doing exciting new things that will change the nature of the construction industry or has the potential to. So this is an article I wrote when I was president, Ventures in 3D, some pictures of you've probably seen these examples. This is by a company called Apis Core. And so it's pretty exciting to see this come out. All right. That leads me to my summary. The summary is this. SCC is a valuable option. It's good, very different than normal concrete, has different behavior, different performance, but it requires specialized mix design, specialized testing, very high attention to quality control, and a high level of expertise with concrete materials. If you are working with a company interested in SCC, you first of all want to have the will to do it. Your management has to believe that this kind of material has great benefit to your company, that opens the door to different kind of projects. But when you do this, you want to do it in partnership with people who have the expertise. And particularly, I would go first to your concrete suppliers who have done SCC before. I would turn to my technical experts from admixture companies who know about SCC, and try to bring that expertise into my own company. There also are students coming out of the university who have done master's and PhD projects on SCC. So the technology is fast becoming part of our community standard experience. I can tell you that there are many different practical building construction projects that show that SCC is used successfully. That is no question. No one doubts that SCC is a valuable material, and a reliable and a durable material when done correctly. And the last pitch I would make is that the ACI partnership you are establishing here with this joint membership is a terrific opportunity. If you don't know about some of the new things going on with concrete, we'll start with this partnership with ACI. ACI has committees on this. And on these committees, you have some of the best experts around the world, really. We always kind of compare where is ACI with regard to RILEM. RILEM is very popular and very impactful in Europe, but they also participate at ACI. So ACI has participation truly from around the world, and Indonesia too, for that matter. Why should we should include everybody? And I think that leads me to the end here. A little pitch of our College of Engineering at the University of Illinois, and I am done. So I'm going to turn it back over to our moderator to take any questions that you might have. Thank you all for listening. It's always a little hard to listen to a long lecture on the computer. Thank you for your patience, and I wish you the best of luck as you take on projects that include SCC materials.
Thank you